64 million people worldwide live with heart failure. That is 64 million people living in constant fatigue, being unable to catch their breath and being unable to concentrate. We want to help. Durham Heart has over 40 students volunteering their time to research a new design for a total artificial heart. Our design includes a mechanical crankshaft, transforming horizontal rotation into the pulsatile movement of two deformers, which pumps the blood out of two chambers at the top of the device. The device is powered by a transcutaneous energy transmission system, or a TET system, transferring energy through the skin and supplying the device with electricity without the need for a driveline, which often gets infected. Testing of a 3D printed prototype has shown the integrated TET system can power the heart with a beats per minute of up to and including 120, without reducing the torque and compromising any mechanical parts of the device. You can see how the displacement of the coils relative to each other affects the power supplied to the heart, with the lateral displacement causing the lowest effect and movement away from the skin greatly affecting the power that is supplied.
Hello everyone, this is a demonstration of Durham Heart TET system where I'll be going through a quick overview of the individual components in this prototype setup and how we are currently assessing the system's efficiencies and its horizontal tolerance. Over here, we have quite a simple setup where we have a DC power supply, a transmitter circuit, a transmitter coil underneath a silicon layer which represents our human skin, a receiver coil, a receiver circuit, followed by a buck voltage regulator, and finally a 22 ohm power resistor, which represents our load in the setup. The way our current setup works is quite straightforward. The transmitter circuit here converts the DC waveform into AC waveforms across the transmitter coil, generating alternating magnetic fields through the silicon layer, which induces voltage across the receiver coil. The induced voltage proceeds to get rectified and then later on step down to about 10 volt and is then fed to the 22 ohm power resistor, leading to about 0.5 amps running across this load and outputting about 4.5 watts. In this case, we can deduce that the current overall TET system efficiency when the transmitter and receiver coils are perfectly aligned is about 36%, seeing how our input power from the DC power supply is about 13 watt. To assess the horizontal tolerance of our system, we set one of the coil, the transmitter coil in this case, as the origin with its side aligning with the silicon layer sides. The other coil will be moved relative to the origin, and its displacement is measured by determining the distance from its edge to the silicon layer side. Through this, we will be able to collect data points across various coil positions to create graphs to visualize our system's horizontal displacement tolerance. In the future, we're seeking to further optimize the circuit's efficiency by assessing different compensation networks, as well as investigate and mitigate areas where there is high temperature rise in the circuit.
I hope you have enjoyed learning more about our design and what we can do to help patients with end-stage heart failure. During this video alone, 5 people have died in the US due to heart failure, so thank you for your interest in our project. And to know more, visit our website or follow our socials.
Thanks for watching, and I hope you look forward to more future updates from Durham Heart.